Okay, so, oh, where's my notes? So today we're gonna do gene stability, which is the stability of a cloud of gas against its own self-gravity. And we might do Heisenberg uncertainty principle if we get there, because Heisenberg's uncertainty principle doesn't have anything to do with quantum mechanics. It only has to do with Fourier transforms, or really transforms. When you have two variables that are related by certain transforms, you get a relationship on their variances that is a general universal thing. It doesn't really have to do with specifically momentum and time, momentum and position, or time and energy. The magic is that momentum and position are Fourier conjugates of each other. That's where the magic shows up when you get to quantum mechanics. The math is just math. So we'll talk about that. Mostly I want to talk about that just because I want to start talking about Fourier space a little bit, because next we're going to do turbulence. And so when we're talking about turbulence, we're dealing with Fourier space quite a lot, because we do a lot of turbulence work in Fourier space because it makes more sense that way. Okay, I'm going to go ahead and get started. So what am I planning on doing? So the first thing I'm going to talk about is so I'll derive Poisson's equation. And this says that del squared phi equals 4 pi g rho. And this is where gravity comes from. So I'm going to show you that because we need it. I don't actually think we need all of that, but it's a useful thing. And then we're going to do gene stability. And we're going to talk about why what I'm going to do is actually a bullshit thing to do, but we're going to do it anyway, because it turns out if you do it the right way, you get the same answer, so it's all okay. But we got to talk about why what I'm going to show you is kind of horse cheese. So we'll talk about the swindle, and then we'll actually do it, and we'll get the gene's mass. And there's a mass and a length. And this part will look a lot like sound waves with an extra term, and you'll see where the badness comes from the extra term. And then 3, we'll do Heisenberg, if I get there. So I did a dirty stunt, and I moved the reading to tomorrow. So the next, because I moved the homework that was due on Thursday to the following Monday, because some of you had said, hey, that's kind of long for as much time as you've given us. So I gave you a little bit more time. But I need to start talking about turbulence sooner, so I want you guys to read the turbulence section. It's not mathematically very challenging, this first bit. You're not probably going to understand it very well because it's weird and confusing. So I want you to read it first, and then we'll talk about it, and we'll talk about why it's weird, because it does take a second to get your head around turbulence, because it gets very abstract very fast. So yeah, let's put those up here. Reading and homework. So there's reading due tomorrow and homework due next week. And I'll have office hours next Monday. And if you're, I strongly recommend you guys start looking at the homework before next Monday, because it is long. So if you're going through stuff and you want to ask questions about the homework, like meta questions about the homework Thursday, that's cool. Or if you want to email me, that's also fine. It's not a super hard homework, but it is a long homework. So a lot of things, there's 10 problems, which is more than I usually put in a problem. Most of the derivations are derivations that you've seen, and I just want you to put your hands on them and go through them and practice doing them. So most of the things are things that you've seen already. That being said, it is a long homework. Okay. So today, the first thing we're going to do is derive Poisson's equation, because Poisson's equation is fundamental. It is how I get gravity as a simulator. If I have a big cloud of gas and maybe there's a galaxy in it, and maybe there's another galaxy over here, and maybe these are all in a big dark matter blob, I have some complicated simulation that contains the whole universe. I need to get the gravity for that. And so what is gravity? The force of gravity as a function of x is equal to, now this is the force per unit mass. Is equal to the integral of g times rho of x prime over r prime squared r hat prime d cubed r prime, where this is the force at some position x from some density distribution that we'll describe by x prime. Okay, there's only one space, it's x. But for the integral, f of x is the point that I get here, and rho and r are the density at a point x prime and the distance between the 2 points. And now here, you'll notice this missing minus sign. I've defined r prime as x prime minus x. So if you're like, wait, gravity's negative. Gravity's negative. Gravity's always negative. But that's what the minus sign comes from. So if I switch the sign of this and I write x minus x prime, then you'll pick up a minus sign. So this is the gravitational force. I'm going to leave that up there, and I'm going to come over here. What else do I know about the gravitational force? How do I get the gravitational potential from the gravitational force? Okay. How are they related? What's the easy relationship between F and phi?
Minus grad phi.
Minus grad phi. So F equals minus grad big phi. This also says the acceleration from gravity, because remember, this is per unit mass, so the force per unit mass is what?
Acceleration.
An acceleration. Force per unit mass gives you an acceleration. So the acceleration due to gravity is just minus grad phi. So what happens if I take div of f? So the divergence of force is equal to the gradient with respect to x. Now I've got an x and an x prime, so I've got to be careful with my gradient. So this is a gradient with respect to x of the integral of rho over r hat squared r hat d cubed x prime. Prime. Everybody's prime. Rho of x prime. So I bring this in here, and I'm left with rho of x prime times grad x of r hat over r squared prime prime. Sorry, that's a div, times d cubed x prime. So I'm operating this integral with grad x. It jumps right past this rho prime because this does not depend on x. Yeah.
Big G.
Oh, thank you. Unlike GR, I use G as not 1 units. In GR, you boost to G equals 1 and C equals 1 and 4 pi equals 1 units. I'm only half joking about 4 pi equals 1. That's actually what I do for MHD in the code. We set all the 4 pi's equal to 1 and just absorb them into the magnetic field because you don't want to have to deal with those things. So anyway, so now we got to deal with this thing in here. So now I've got grad x of x prime minus x over x prime minus x cubed. Okay, why did I write it this way? Because this is r hat over r. And what's r hat? R hat is R over the magnitude of R. So this gives me an R over R cubed. That's the same as this R hat over R squared. Does that make sense? So the derivative with respect to x of x prime minus x over x prime minus x cubed is equal to 3 over x prime minus x cubed. Okay, we got a quotient rule. Quotient rule is just product rule. So it's the derivative of the top divided by the bottom times the derivative of the bottom times the top. So the derivative of the top, what is the divergence of x? So this is dx plus dy plus dz. Which is what is? What's that? What is dx by dx? So what is this expression? 3. 3. So that's where this 3 comes from, because the divergence. And when I was preparing this morning, I stared at that 3 for a good 4 minutes, and I was like, "Where did this 3 come from?" Hadn't had any coffee yet, but minus the top times the derivative of the bottom, which is 3 times x prime minus x dot x prime minus x over x prime minus x to the 5th. So now what happens if x is not equal to x prime? Then this part here is x prime minus x squared. And that cancels out 2 of these, and I'm left with 3 over, let's call this delta x cubed minus 3 over delta x cubed equals 0. So here I have a function that is 0 everywhere, except for the origin, where I don't know what it's going to do. What kind of thing does that? The delta function. So this is going to behave like a delta function, but I'll show you why. So this thing is 0 except at the origin. So because of that, I know that this integral is only going to deal with the point at the origin, and everything else is going to come out. So this is equal to g times rho of x times the integral of grad x. And now I'm going to do a stunt. Because this is symmetric by a minus, or this is anti-symmetric, I can change this x to an x prime and I pick up a minus sign. Does that make sense? Times r hat prime over r squared, r prime squared, d cubed x prime. And now I have a full derivative inside a volume integral. What do? Gauss's law. Make it a surface integral, right? But now I can deal with this for r prime, absolute value of r prime is less than some tiny little value, because I only need to worry about this integral in a tiny little sphere around the origin, right? Because that's the only place that it's defined. So we turn this into then, now I've got minus g rho times the integral of r prime equals epsilon of r prime over r squared. Now, okay, what is d cubed r? D cubed x prime is equal to r prime squared times d omega. Does that make sense? This is just my volume integral. Since I'm on a surface now, it's just whatever r prime squared is, and then d omega is my solid angle element. Stop me if this doesn't make sense. So this turns into r prime over r prime squared times r prime squared d omega, which just turns into minus g rho times the integral of hat. So this hat, we dot this hat into my surface element, so so that's how this works. I think actually my r hat is gone because I've already dotted it into my surface element. My r prime squared, and I'm left with just d omega. R hat doesn't contribute anything but direction, so we've already taken care of that on the surface. So this turns into just an integral over d omega, and what is the integral over just solid angle? 4 pi. So this equals minus 4 pi g rho, which is equal to grad phi, which is equal to minus grad phi. So then we're left, this becomes minus del squared phi. So we're left with what we set out to prove. We can just erase these minus signs. 4 pi g rho is equal to del squared phi. So this is, so when I'm simulating something like this, I think I trailed off and got distracted. So when I'm simulating something complicated, I can say that f equals g m1 m2 over r squared, where m1 and m2 are tiny little mass elements. But that's really, really complicated and really expensive to do. What I can say instead is I know my density field and I know my potential. And I know that they're related by Poisson's equation. And this is actually very easy to solve with Fourier transforms. Why is this easy to solve with Fourier transforms? Because if I have del squared phi equals 4 pi g rho, if I just take the Fourier transform of both sides, I'm left with k squared phi equals k squared phi hat equals 4 pi g rho hat, where phi hat is the Fourier transform of the potential and rho hat is the Fourier transform of the density. And k is just a number, that's just the value. So then my potential, phi, is just equal to rho hat of k over phi hat over 4 pi g on the top over k squared. And then I'm done. So then I just have to Fourier transform this back and I have the potential. And then I take differences of it and I get the derivative of the potential. Or I could just multiply by k and get the accelerations in Fourier space and then Fourier transform back and get spectral accelerations. Is there anything else that I need to say about that? So anyway, del squared phi is 4 pi g rho is a crucial description of the universe. And we'll need it and we'll come back to it, and all it says is f equals ma and f equals gmm over r squared. So now we're going to go talk about what happens when I have a big ball of gas. So this is going to look just like sound, like our derivation of sound waves, except instead of just the pressure on the right-hand side, we're going to have the gravitational acceleration. So let's start that off. So we start off with d by dt of rho plus div rho v equals 0. That's continuity, and that doesn't ever get changed unless you have a source of material. And then d by dt of v plus v dot grad v equals minus 1 over rho grad p. And we'll just make this c squared grad rho, because we know that our perturbations are adiabatic. Well, we're going to assume that the perturbations are adiabatic. When a gravitational cloud is collapsing, I don't think there's anything that's actually adiabatic about that, but we're just at the initial stage. This doesn't follow, here's an important thing, this doesn't follow the whole nonlinear evolution of the process yet.
Are those partials? Or?
Yeah. Oh, this should be partial. Yes. Thank you. Minus grad big phi. So when we did sound waves, we linearized around rho naught equals a constant and v equals 0. So I'm going to talk about the gene swindle. I'm also going to prove to you that the universe has to be expanding in one swoop, which has bothered scientists for a long, long time. People have been really bothered by this. So if density is a constant and the initial velocity is 0, then let's just look at Euler's equation. The left-hand side becomes 0, and I'm left with minus c squared over rho grad rho equals grad phi. So if rho naught, so I'm going to assume that this is true and use it anyway, even though I'm telling you that rho naught is a constant. If rho naught is a constant, what is phi naught? Also a constant, or 0. So if phi naught is also a constant, what's my gravitational acceleration? 0. So, okay, so if my universe is basically homogeneous, then there is no gravitational acceleration from it, and there's no gravity. Or, so what this says is that this side equals 0. That means that the gravitational potential also has to be effectively 0. There's a constant that you get out of the gravitational potential, but it doesn't matter.
So you went from 1 over rho grad pressure to
Right.
c squared grad rho?
Yeah.
Okay.
Yeah. So this is, so then when we go to linearize it, sorry, my narrative flow is not where I want it to be for this part of this problem. The basic stunt is, if I'm going to assume that rho naught is a constant, then so if rho naught is a constant, then phi naught has to be 0, and my universe is empty, and there's no gravity. Or it can't be accelerating. So we run into this paradoxical problem where if I'm assuming my density is constant, then my gravitational potential is not well defined. And so what this means is the upshot of this, sorry, that preamble kind of sucked. I'll come back and try it again next time. Is that the universe is either infinite and homogeneous, or so we have these three things. The universe is infinite and basically homogeneous, so that means there's no particularly special place in it. It has some stuff in it, and it's not really accelerating. Only two of these can be true at the same time, because I have these two equations, and I'm going to set a bunch of things equal to 0. So the universe can either be homogeneous and has stuff in it, in which case it is not static. It has to be expanding or contracting. Or if it's static, then it either can't be homogeneous or can't have any stuff in it. So if you have a static universe that's not moving, then it either has to have an edge so that there's an actual gradient to the gravitational potential, or it's empty. So if it's empty, that's boring. So the basic idea that we're starting with, that we can start with a uniform, homogeneous, constant density and then perturb that, that's the swindle, because that doesn't actually make any sense when you look at the equations. But what you can do is say, okay, we'll do all this on a thick slab of stuff where phi is non-zero here and phi and rho is 0 outside, and we'll do the same perturbation theory on this thick slab of stuff and then send the slab size to infinity. You get exactly the same answer. So we can fix it. So we're going to run with this thing that's a little bit ill-defined, but we'll we'll run with it anyway. So the first thing I'm going to do things in a slightly different order than what I did before. I'm going to do the Fourier transform business first. Oh, actually, I got plenty of time today, so I'm going to go off on kind of an aside and show you something. So I have this equation before I go into the meat of this. d by dt of v plus v dot grad v equals minus c squared over rho grad rho. Let's just say that for a second. So what we do in a lot of these things, and let's call this 1, 1, 1, 1. Now, normally we would throw this out because this is a square term, but let's keep it for a second. And I'm going to say that v1 is equal to e to the I k x minus omega t times, let's call it a of k, where a is then my amplitude in Fourier space for all of my modes for my velocity. D cubed k. And then rho 1 is going to be the same thing, e to the I k x minus omega t, b of k, dk. Does that make sense? So I'm just writing down my velocity is a Fourier transform of whatever my velocity is. I'm going to call this v hat. And I'm going to call this one rho hat, because that's easier for me to keep track of. Does that make sense? Does everybody have a, yeah?
In the v hat is the velocity in Fourier space?
That's right. So v hat is the velocity in Fourier space.
Okay.
Or it is the amplitude of each of the Fourier modes. Those are the same sentences.
Yeah.
Right. So what we normally do is we have d by dt of v1. We throw out this term equals, I'm just going to call this a times d by dx of rho 1. And then I plug in these two equations. And so now what we normally do with one of these is we just pick one Fourier mode and run with that. And I'll show you why that works. And so this isn't, a lot of times people will say, as an ansatz, as a guess, we're just going to guess that a Fourier mode is going to solve this equation. And that's not true. It's not a guess. It's much more powerful than that. It's taking this and plugging it into this equation. So this equation then becomes, I'll go over here. I don't need any of you. So if I just take these two guys and I plug them into this equation, I'm left with d by dt of the integral of e to the, I'm gonna call I k x minus omega t equal to big delta, I big delta, just for shorthand. This delta is, this isn't like standard or anything. I'm just going to call it delta because this makes my board style easier. E to the I delta times v hat dk plus equals a times d by dx of the integral of e to the I delta rho hat of k dk. Yeah.
So that'd be dq. Oh no, we put it in 1D.
Yeah, we're in 1D right now.
Okay, yeah.
You can make it d. Oh, sorry. Let's just be in 1D. It's a nice thing about a lot of geometry is you can move between 1D as long as you prove it generally enough. You can move between 1 and 3D. Yeah.
Where did you get the A formula again? Is that
This.
continuity?
Yeah, this is just continuity, but I'm throwing out continuity here, but I'm throwing out this term and I'm just going to rewrite this crap here as A because I'm lazy. So this is just the same thing as the continuity equation. So I can take all of this stuff, because this is the same as this, so I can shove all this stuff to one side of the equation, and I'm left with the integral of, let's apply this d by dt here, and I get an I omega t, no, just an I omega minus I omega v hat plus I k a rho hat dk equals 0. Okay, so I'm just doing this on that, doing this on that, and then putting everything the other side. And then since I have this thing that's inside of an integral, and the integral is 0, and this thing is not positive or negative. You don't know what this thing is, but you know that the integral area is arbitrary. Since the integral is 0 for whatever integral bounds I take, the inside is equal to 0, and I'm left with minus omega v hat plus k a rho hat. And then you can proceed on with the derivation. So now I've got an OV and a k, so I'll have to use the other equation to get rid of one of the variables, but the process is the same. But I'm left with just my Fourier mode, right? So now I can pretend that I'm just dealing with one Fourier mode because I got to get rid of the omegas and stuff. Does that make sense? This is a little bit complicated, but instead of just saying v equals v hat e to the I k x minus omega t, and just saying that I'm picking one, we're using the whole machinery of the Fourier transform, plugging it into the equation, simplifying, and we get to where we would have started if we just said, oh, I'm just going to pick one. It's the same thing. Where does this fail? This fails if I'm going to keep this v1 dot grad v1 term. So when I have this term, if I'm going to plug in the Fourier transforms of that, that's going to look like e to the I k x minus omega t times v1 of k dk dot grad integral of e to the I. Now I have to use a different integrating variable. I can't use k again because I'm going to mix these two equations again. So the integrating variable, if I have two integrals, the integrating variables have to be different if I'm going to multiply them together. So this is e to the I px minus gamma t times v of p and t dp. So I shove all of this stuff into one integral again, and I'm left with the integral of e to the I k minus p blah, 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 and then a v1k, v1p, dk, dp, and I have this term that is the interaction between waves of different sizes. So k and p are different wave modes, and they have to be different wave modes because they come in multiplied. So if I'm going to do the same linearization but leave the Fourier term in, then I have this term that looks like collisions of waves. So another way to think about all this linearization business is to assume that things in Fourier space don't collide with each other. And if they do, then you have to deal with that process, which is interesting, but beyond what we want to do. So there's all of this machinery that we're doing when we just jump through, when we just skip past stuff, because it works. So I'm going to take these two equations. Okay, that aside is done. Now we'll do genes. So remember what we do. So we have a background solution. You linearize. You drop in the Fourier modes. And you get a dispersion relationship. I had a much longer way to write these things down before because I left out all this, because I left in all the steps. But these are the basic things that you're looking for. So we're going to start with some background solution, which you always need. You can linearize it, Fourier transform it, and then get a dispersion relationship. And these two are take the most bits. I'm actually going to do the Fourier bits first, because this is actually how the book does it. I could do it in the other order like we did with sound waves. But I'm going to do the Fourier stuff first. So let's start with this equation. So for the Fourier transform, d by dt equals minus I omega, and d by dk equals I k.
D by dx.
Oops, x. Thank you. D by dx is ik. So we drop that into this term, and I'm left with minus I omega rho hat plus k rho hat naught minus rho hat 1 v1 hat. K is multiplying all of these things. That's a dodge because of the things I did out on the other board. So we need to replace this real quick with rho hat naught v1 hat and throw out the other term. Equals 0. Because if I expand this out, then I'm going to get a rho 1 v1, and I get to throw that out. And then from Euler, I'm left with minus I omega v hat plus this term is going to be a v1 and a v1, so we'll throw that term out. Equals minus c squared over rho naught k rho minus k phi. So now in everything that I'm doing, v hat and rho hat, this is a rho hat, and that's a phi hat.
Eyes.
Was that?
And the eyes.
Oh yeah, and then we have i's, but everybody gets an I, so all the i's cancel out. Okay, so now, how does phi hat behave? So I know that del squared phi equals 4 pi g rho. So this becomes k squared phi hat equals 4 pi g rho hat. That make sense? So this is Poisson's equation that we just solved. We do that in Fourier space, and the graph becomes a k squared, and everything becomes the Fourier mode. And then let's move over here. So now, oh, did I really? Oh no, here. Here, I'm going to cheat because he did the algebra, and I'm going to mess it up. Okay, so over here, we're left with a minus omega rho 1 plus rho naught k dot v1 equals 0. And the k dots into the v1. That doesn't matter because we're in one dimension, but that's how it would work. And then the other one, which is minus rho naught omega v1 equals minus c squared k rho 1 plus rho naught k phi 1. Does that make sense so far? So now I'm just going to eliminate a term. So you cross multiply and add them together, and you're left with, let's see, you do a little bit of algebra, then that's boring, and you're left with omega squared equals c sound squared times k squared minus k genes squared, where k genes squared equals 4 pi g rho naught over c sound squared. So it's all the same process that we did with sound waves. So when we got here, when we did sound waves, this term wasn't here. This term is the phi naught term. It has the g in it. So this term wasn't there, and we got something that had a constant phase g. But now I've got something that has this negativeness to it. So this tells me two things. So it tells me, first, it tells me how a wave will propagate if there's gravity. It will also tell us that things go south if k is smaller than k genes. So everybody see why? Because if this side is negative, then omega is imaginary, and then things blow up. So you have this gene's wave number. K genes squared equals 4 pi g rho naught over c sound squared. A length, let's call it a lambda. Lambda equals 2 pi over k. So the gene's length, let's call this LG. L genes is equal to C sound L genes squared. C sound squared over G rho naught, and then there's a, that's upside down, and there's a 2 pi, which cancels a 2 pi, and then another 2 pi, Just love the pi. Okay, so I'm going to write this down over here in orange. So the gene's length is equal to pi times c sound over the square root of, gene's length squared is equal to pi c sound squared over g times rho naught. So this tells me what the smallest thing, or what the biggest thing is that's stable against gravity. So now I'm going to do the cheat way real quick again. So this is how I started last class, or this is how I ended last class. So if I have a blob, it has a size L, and I have the crossing time is equal to L over C sound, and the free fall time is equal to 1 over G rho, square root of that. Does that make sense? So this I didn't prove, but we did it. You can do it with dimensional analysis, and this is probably going to be a homework assignment with dimensional analysis. It's probably also going to be a homework assignment to do with Kepler's law, because it's really not all that hard. It's just a little bit of algebra and setting up the problem properly, but that's relatively painless. I wouldn't say easy, but not super hard. The basic idea to prove this is you start with a sphere of uniform density and think about a point on the edge, and then you treat the mass as all being contained in the center, and you know this is going to be on an elliptical orbit, and you know it's going to stop at half of that. So you know the period orbit relation from Kepler's law, from taking Intro to Astro with me or wherever. So you know how long this will take to go around because of Kepler's law. So you just figure out how long it just takes to go here and splat, because that's what will happen. And then you get a 3 pi a 32, but other than that, you get this answer. So if I equate these two things, I get the same thing. If I say that T cross has got to be less than T free fall, then that says that L has got to be less than C sound over G rho, square root of G rho. And we get, let's square it, C sound squared, and let's get rid of that. So we get the same answer. L squared is C sound squared over G rho. You get the same answer that we got using this much more heavy mathematics. So that's very satisfying. It's nice when dimensional analysis matches the heavy mathematics. So, how is sound speed and temperature related? Does anybody remember off the top of their head?
Square root, or gamma kVt over m.
So I got a gamma kt over m times temperature. So the sound speed squared is proportional to the temperature, because remember, sound speed squared equals dp d rho, and you know p is rho to the gamma, and you know PV equals nRT. So the sound speed is just proportional to the temperature. I haven't heard from that guy in a while. I'll put that over there so I'm not distracted by my texts. Sorry, that totally derailed me. Where was I going with this? I think that that's all I had to say. So this is basically how clouds collapse. So if you have a cloud of gas with a certain temperature and a certain size, you can tell if it's going to collapse or not. If I have a cloud with a certain temperature, I can tell how big of a star I'm probably going to form from that. So the other thing that you can get is the gene's mass, which is 4/3 pi times the gene's length cubed times rho naught. And you get, I wish I were really good at doing algebra in my head, but I'm actually really bad at it. And you get 4/3 pi to the 5/2 kt over gm to the 3/2 rho naught to the -1/2. So it's a little bit hairier, but the only thing that you really need to remember is t to the 3/2 over rho to the 1/2. And the rest are constants that just make everything make sense. So the mass of a cloud is determined by the length and the density, or the gene's length and the density. So if I have a cloud of 100,000 solar masses, and it is at 10 Kelvin and has a density of 100 particles per cubic centimeter, you can sort out the mass of the typical star that it's going to form. It's going to be this. If you go back in time, you can do the same stunt and say, I have the early universe, how big should a galaxy blob be? And you get a similar answer. Now in the expanding universe, you need to do this again, where we add some a dot over a for the expansion of the universe. You got to add the expansion of the universe in there to do it right, and this answer changes a little bit, but not a ton. Okay. So that is genes. Does anybody have any questions about genes? Did it all make sense? Okay. Okay. The last thing I'm going to do is kind of change topics a little bit, and then if that doesn't take me all that long, then I'll start talking about turbulence. But let's talk about Heisenberg for a second. This is more Fourier stunts. Okay. So, and this is just some math, so please stop me if this gets confusing. So f of x is equal to f hat of k e to the I k x dk. Fourier transform. We're going to Fourier transform. And now we're only in one d and one variable. So, whereas before we were actually in 4 dimensions, which makes things a little bit hairier, but really not all that bad. So I'm going to say, so we're going to say, and this is the only contact that I'm going to make with quantum mechanics, is that f squared of x is a probability. The fact that it's squared is the probability is the magic in quantum mechanics, and don't think any further about that. It's a probability when you square it, and that's what the wave function does. So f squared is a probability. So then what is the average of x? So let's not put that line there. Let's erase that glitter. So this is f of x. How do I get the average position of this blob? If f squared is my probability.
So we're looking for the average of f or x?
X. Let's talk about the average of f. What's the average of f?
Totally half
What's that? No, no, this, not so complicated. Just think about an integral. So the normalization of f, the integral of f squared dx, we're going to assume that it's normalized to 1. That means that all the probability adds up to 1. To find the average of x, I'm going to look at the integral of x times f squared dx. Does that make sense? Is everybody on board with this is the average? So what are you doing? You're taking each position and you're multiplying by how much of that you got. So this is just like if I was going to find out the average, if this is now p of height, and this is height, if I wanted to know what the average height of people in the room are, I would take all the people and add up all the heights and divide by the number, right? Or I can take all the heights and multiply by the number of people with that height. That saves myself some time. That way I'm integrating over height and not people. Because there's like a billion people, but height goes from 0 to 6, right? This is the same thing. It's just x times the probability that I have that x, and then we add that all up. And now you don't have to divide by the number. We took care of that by making sure that f squared adds up to 1. Does that all make sense? So a lot of times, the average of f doesn't matter. So let's say, so we're going to assume without loss of generality, I can assume that I have unit norm and the average is 0. So I can assume these two things. So here's 0. So the average of this function is 0, and nobody cares about that. How do I describe this function, this distribution, within something that doesn't suck? So I want to know the average, it's 0. That's a Born quantity. And that's true for any distribution. That's true for any probability. The average of the quantity is usually not as interesting. What's more interesting is the average of the square of x. So, and how do I write that down? That's x squared, f squared of x dx. This is called the variance. Does that make sense? This is the quantity that I need because that's the variance actually describes this distribution. The mean doesn't describe the distribution because really you can slide the mean wherever you want, just add a quantity to it. The variance describes how broad the distribution is, and that's really the quantity that matters a lot more with a lot of what we're doing. So you have a variance in f, and you have a variance in f hat. And we're going to make some assumptions. We're going to assume that they're all equal to 0 in mean, and x has, the mean is 0, and we're going to assume that the variance is 1. I can just do that by changing the units of the problem to make it look like what I want. So now I'm going to go over here and start with a fresh board where my board management doesn't suck. Okay. So f of x equals the integral of f hat of k e to the I k x dk, and we're going to assume that the average of x, which is the integral of x f squared dx, equals 0, and the variance of x, which is the average of x squared, is equal to the integral of x squared f squared dx equals 1. This is something that I can just do by changing the units. So this is, I'm just going to assume this because it's free. I can make any function, any distribution that I do have, I can make look like this. We'll also assume that the integral in k, which is k f hat dk, is also equal to 0. This is also a thing that I can do. Changing the integral of, changing the average of, sorry, scratch that. That thought was not relevant for here. Okay, so then our moments, average, let's call this sigma squared x is equal to the integral of x squared f squared of x dx. That's got to be squared. And sigma squared k is equal to the integral of k squared f hat squared of k dk. So this is the variance in k space, and this is the variance in position space. So this is how wide it is in real space, and this is how wide it is in spectral space. So if you're thinking about a communications stream, this is the variance of the signal, and this is the bandwidth of the signal. So this is how many frequencies are participating. This is the breadth of frequencies that are participating in this signal processing experiment.
So, sorry, there's Fourier space and
Real space.
real space.
Yeah, or position space.
Okay.
Okay, so okay, so A dot B is an inner product. That's for vectors. I have a function space, so the inner product for two functions is the integral of g times h dx, and this is the inner product of g and h, and we write this with angle brackets typically, and g comma h is the inner product of g and h. So there's this thing called the triangle inequality. That's the thing I need next, right? Oh no, I need another thing. Well, let's go with that. So the triangle inequality. How many of you have seen the triangle inequality somewhere before?
Never heard of it.
Never heard of it? It's really simple. It says that the hypotenuse is shorter than the sum of the two sides.
Oh. Oh. Okay. Well, yeah.
Right? Or A dot B is got to equal less than or equal to A dot A to the 1/2, B dot B to the 1/2. So the dot product is less than either of the two lengths. Does that make sense? So this is like the dot product, and these are the two sides. So the dot product between the two, between any two vectors, is less than the product of their magnitudes. Was that?
Isn't the dot product like the projections? Like which two? I'm just confused about your A and B.
Yeah. So. Yeah, let me try a better triangle. So let's get a dumber triangle like this. So if this is A and this is B, that's A dot B, or that's A dot B. It's symmetric. So that size is smaller than the product of the two lengths. So the dot product has to be shorter than either of the two vectors, is where it comes down from.
Okay.
Right. Right. You can't project a vector onto another vector and get a vector that's longer than both of the vectors. It's got to be shorter than both of the vectors. I mean, I could take a really long vector and project it onto this really short vector, and I get something like that. But the inequality still stands. So I have a similar inequality a similar triangle inequality for this vector space that is now functions. And I can say that the magnitude of the integral of g times h dx has got to be less than or equal to the magnitude of the integral of g squared dx to the 1/2 times integral of h squared dx to the 1/2. So this is just saying that the projection is shorter than both of the sides. In this, now a dot product is an integral between two functions, but that's fine. That's not a big deal. So, okay, so where are we and what have we done so far? So, we have a function and its Fourier transform. We've talked about the average and the variance, and the average in Fourier space. We've talked about the variance of both of the quantities. So now we're going to do a little magic, and we're going to say that g is equal to f times x, and h is equal to f prime, the derivative of h. So there's another equality that we there's another inequality that we need. Sigma squared k is equal to k times f squared dk, k squared f squared dk, which is equal to, we're just going to turn this. So I've got k times f hat. I've got k times f hat. And what is k times the Fourier transform in real space? We did it a whole bunch when we were doing genes, but backwards. There you go. So this is the space derivative. So k times f, okay, there's an I in there, but that's okay, it's all squared. So this is equal to I k f hat squared dk, and this is just equal to f prime squared dk. So we'll need this in a second. So then we take these two test functions and we plug them into the triangle inequality, and I'm left with the integral of x f prime. And this is a thing that I'm inventing because I'm going to need it, because this will turn into things that I do want. X f prime dx. Okay, I can just integrate this by parts, and this turns into the integral of x times 1/2 the integral of f squared prime dx. So that's one side. The other side, I'm going to use triangle inequality on this. So this way is just integrating by parts. This way is using this triangle inequality that we wrote down. And this says that the integral of x f prime is less than the integral of x squared f squared dx to the 1/2 times the integral of f prime squared to the 1/2. This, so now I've got these two expressions. And this one, so this is sigma x squared times sigma k squared. See, so I've got sigma k squared is the integral over f prime squared. That's this guy. And this is sigma x squared f squared, which is just this guy. And so what's the right-hand side? This has got to be less than or equal to, this is less than or equal to, this thing is less than or equal to this thing. So this I get from just integrating, and this I get from the triangle inequality. So I can just do this integral, and this integral, you do a little bit of algebra, and this turns into I can just integrate this by parts again, and integrating this by parts just gives you a 1/2. Why is that? Let's do this over here. So I get a 1/2 integral of x f prime squared dx. I integrate that by parts, and I get a first thing times the derivative of this second thing, and this turns into the integral of x squared f squared. Is that right? Where did I lost myself? At the endpoints. Sorry, x squared f squared evaluated at the endpoints, because we're doing an integral. I'm integrating this by parts. So I integrate this by parts, and I get x squared f squared minus the integral of f squared. And this is 0 because we assumed it was going to be 0. And this is 1 because we assumed it was 1. And so this whole integral just gives me a 1/2. So I just integrate this guy by parts, and I get a 1/2. And so then what I'm left with, when I pick up all the pieces, I get a 1/2 on the left side, and I got a sigma x sigma k squared. So I'm left with, let's do it in yellow. 1/2 is less than or equal to sigma x squared sigma k squared. And we're done. So what does this say? This says I've got some distribution in real space. And in k space, I have some other distribution. I want to draw this one tall and narrow. So the width of this one is small, but the width of this one is big. And the product of the widths of the distribution in Fourier space and the distribution in real space, the product of those two widths can't get arbitrarily small. Why is that? That's another way of saying a plane wave is infinitely long. So if I just have one frequency, that has to go on forever because I can't stop it without introducing new frequencies. Does that make sense? If I just I can't make a tone that does this forever and then stops because it'll ring. That's what this is saying. This is saying that I can't have a plane wave that goes on for a while and then stops. You have to introduce shorter wavelength things to get it to stop. You have to introduce more harmonics to get it to stop. So this is why we talk about bandwidth when we talk about digital signals, because the width of the Fourier space tells you how much information you can carry. Yeah.
Isn't that fact kind of like obvious just from like thinking about waves in general?
Yeah.
If you're like, doing this string like this, it's gonna be the same thing as long as you keep doing it like that.
Yeah, but as soon as you do something different, it's going to change, and as soon as you need it to change, you have to do something different. So you have to have some other frequency component to get it to start and stop. So it's kind of obvious, but then you put the math with it, and then you have a powerful statement like, just how wide can one of these two distributions be? So this is a statement about how wide the spectral distribution is based on the real space distribution. So this has an enormous amount of power. Now when you get to quantum mechanics, K is the momentum. And that's the magic of quantum mechanics, is this insight that K is the momentum. And it comes from the same crap that we've been doing. It comes from a derivative that turns into a K, right? You get a wave equation and there's a K and it turns into your momentum. So in quantum mechanics, this is still space, but this becomes momentum. But the magic comes from the fact that the real space position of something and its momentum are related by a Fourier transform-like quantity. Similarly, energy and time are related by some Fourier transform-like quantity. And they're all related, and ultimately they're all related by symmetries that you can learn from Noether's theorem. Have you guys learned Noether's theorem yet? A little? Noether's theorem is, I think, maybe the most beautiful thing that anyone has ever done. You'll note I said that about Fourier transforms too. But Noether's theorem gets us the relationship between symmetries in the problem and conserved quantities, the things that are related are also the duals with each other. So spatial symmetry gives you momentum conservation. That's because this is the relationship. Time symmetry gives you energy conservation because time and energy are also related by this way. But the math is really simple. Okay. Okay, let me talk about turbulence for a second. So when I'm just going to set things up for what's in the reading. So the basic idea is this v dot grad v term makes the solutions to any of these things impossible, and it makes everything really hard. So we have to start doing everything statistically. And we have to do everything in Fourier space, which is why I wanted to go through all of this, because this is statistics and Fourier space. So the basic idea is that when I make a large scale motion, I have little tubes of vorticity. And if I pull on it, and this is a homework problem, and I may or may not go through this derivation. If I take a tube that's spinning and I pull on it, what happens? Oh, that's a hard question. If I take a block of silly putty or whatever other slime, and I take the two ends of it and I pull on it, what happens to the middle of it? Well, imagine I'm in space, so ignore gravity. Just pull on it,
It gets thinner.
it gets a lot thinner because of conservation of mass, right? Mass is conserved, so length times width times length times width times height, or length times area is constant. So if I make the length long, then the area has to go down, right? If I do the same thing to a tube of vorticity, I get the same effect because vorticity is also conserved. Remember doing that from Kelvin's vorticity theorem. Vorticity is conserved, so if I have something spinning and I pull on it, the area goes down. What happens to the rotation rate?
Increases?
It goes up. So it's equivalent to conservation of angular momentum. So when I have some little blob of stuff that's spinning around a little bit, and I have some bigger blob of stuff that's also spinning around, so when you have a turbulent system, you have large motions, and then small, and then medium-sized motions, and then motions smaller than that, and then motions smaller than that. You get this hierarchy of motions. So when you have a large-scale motion pulling on some small-scale motions, you get more small-scale motions. So turbulence has this way of taking large-scale energy and dropping it into smaller and smaller and smaller scales of energy. And this winds up giving you a spectrum. If I look at energy as a function of wave number now, so now this is wave number, so this is small stuff over here, and this is large stuff over here. I dump energy into my system, and it will cascade down to the small scale until it reaches the molecular level and starts to dissipate. And we get this power law, where this is linear in log space, where the energy there's less and less and less energy as you get to smaller scales, but you get the whole distribution is populated all the way across. So we'll talk about that, and we'll talk about getting at, I can show you a problem that if you can solve it, you will be famouser than famous. You will certainly win the Nobel Prize. If you can do it before you're 40, you'll win the Fields Medal. So I'll show you that. Probably, I'm not going to get to that probably Thursday. That's probably going to be next week where I actually show you where the problem is. But this is exciting business because this is the mess that actual research comes from. So, all right. And also, turbulence is going to be a problem in almost whatever research you're doing, unless it's nuclear or particle physics. So if you're doing anything other than smashing two particles together, turbulence will be a problem. So, okay. Talk to you soon. See you next week. Reading tomorrow.